We're about to dive into some of the toughest math problems you've probably ever seen. But here's the twist. They weren't designed for university professors. Nope. They were designed for some of the brightest primary school kids in India.
So, I've got to ask, think you're good at math? Think you're smarter than a fifth grader? Well, these next few puzzles are really going to put that to the test. Let's see how you do.
So, where do these problems even come from? This is our source, a textbook from the Association of Mathematics Teachers of India. It's jam-packed with questions from their national math competitions. So yeah, this is the real deal.
Okay, our first puzzle is a great one. It's not about doing a ton of heavy calculations. It's about seeing shapes in a really clever way. It's what I like to call a visual trick.
Just take a look at these two shapes, A and B. What does your gut tell you? Which one has the bigger shaded area? Your intuition might be saying they're pretty close, maybe even exactly the same. But your intuition might just be wrong.
So here's the actual problem, the way the students would see it. It asks for the ratio of the area of figure A to figure B. And just so you know, the distance between any two dots, up or down, left or right, is 1 unit. Now the key here is to not reach for some complicated geometry formula. The secret, the really elegant shortcut, is to just break these weird-looking shapes down into simple little squares and triangles that we can easily measure. Watch how simple figure A becomes when you just draw in a few lines. See? It's really just a 2x1 rectangle, a 1x1 square, and 3 small right-angled triangles. That's it. So let's add it up. The rectangle has an area of 2. The square has an area of 1, and the 3 triangles, well, each one is half a square, so they add up to 1.5. That gives us a total area for figure A of 4.5 square units. All right, now for figure B. It looks kind of complex, right? But it's actually even simpler to break down. It's just 2 right-angled triangles on the ends and a parallelogram, you know, that slanted 4-sided shape in the middle. The 2 triangles together make 1 square unit. And the parallelogram is also 1 square unit. So the total area is just 2. So the ratio is 4.5 to 2. Now we don't really like decimals in ratios, so we just double both sides. And that gives us a final ratio of 9 to 4. That means figure A is actually more than twice as big as figure B. Bet you didn't see that coming, did you? Okay, so that first puzzle was all about seeing the simple pieces inside a complex shape. This next one is totally different. This one is about seeing a simple truth hidden inside a ridiculously complex calculation. It requires what I call a logic leap. So the question is there a natural number n out there where n times the next 3 numbers in a row equals this massive number? It sounds like you need a supercomputer to even start checking. But here's the thing, you don't.
And here it is, straight out of the textbook. This is exactly what the students were up against. But again, the key isn't calculation. It's a fundamental property of the numbers themselves. Okay, so first, just so we're all on the same page, what are consecutive integers? They're just whole numbers right next to each other on the number line. You know, like 3, 4, 5, 6. Simple as that.
All right, now here's the key insight. This is the whole trick. Pick any 4 numbers in a row. Go ahead, try it. 1, 2, 3, 4. Or 10, 11, 12, 13. You will always have at least 1 even number in that set. In fact, you'll always have 2. It's impossible to avoid it.
And what happens when you multiply something by an even number? It doesn't matter what the other numbers are. Odd, even, whatever. The final product must be an even number. That's a fundamental rule of math.
Now let's look at our target number again. What's the last digit? It's a 3. And any number that ends in a 3 is an odd number. And right there, we have a direct contradiction. So let's put it together. We know our product has to be even, but the target number they gave us is odd. Therefore, no such number n can possibly exist. We just solved it without a single calculation. Now that is the beauty of logic. All right, for our final puzzle, we're going to use another powerful tool for cutting through complexity, spotting patterns. This is the strategy you use when a calculation just seems impossibly large.
So here's the challenge. Find the last digit of 2 to the power of 2015. I mean, if you tried to type this into a calculator, it would probably just give you an error message. The number is astronomically huge, so there has to be a better way.
The textbook calls it the units place, which, is just a formal way of saying the very last digit of the number.
Let's just forget about 2015 for a second. Let's calculate the first few powers of 2 and look only at the last digit. Okay, 2 to the power of 1 is 2. Then we get 4. Then 8. Then 16, so the last digit is 6. Then 32, hey, the last digit is 2 again. Then 64, the last digit is 4. Do you see it?
The last digit just cycles through these 4 values over and over and over again. 2, 4, 8, 6. And then it repeats. This totally predictable cycle is the key to solving this whole thing.
So, since the pattern repeats every 4 steps, we can figure out where the 2015th step lands just by dividing 2015 by 4. And we're not actually looking for the answer to the division, we're looking for the remainder, the number that's left over.
So when you divide 2015 by 4, you get 503 with 3 left over. That remainder of 3, that's our golden ticket. It tells us that the answer is going to be the third number in our repeating pattern. And the third number in our cycle of 2486 is 8. And that's it. That's our answer. A simple little pattern just solved a problem that was impossibly huge.
So, we've broken down shapes, we've used pure logic, and we've spotted a hidden pattern. What do all these different approaches really tell us?
For me, the big takeaway is this. This kind of math isn't about memorization or about being a human calculator. It's about developing a mindset. It's about problem solving, creativity, and finding those elegant shortcuts. Really, it's all about learning how to think.
And that kind of leaves us with a final thought. If a seemingly impossible math problem can be solved just by breaking it down, using some logic, or finding a hidden pattern, well, what other big challenges out there are just puzzles, waiting for a new perspective? Something to think about. Thanks for joining me.